In this video, I want to walk through some of the common reactions that we see when we talk about cannabis chemistry. And we're going to start with one we've talked about quite a bit already, which is the decarboxylation reaction. This is a key step to processing plant material or cannabis concentrates to essentially take the THCA, which is the carboxylic acid version of THC, and remove a carbon and two oxygens to form THC, which is more psychoactive. So I have the reaction written out here as line structures. And we can see on one side we have THC A, and on our product side we have THC. The chemical formulas for this, and the way I would structure my chemical equation would be to write out the chemical formula of THCA, which is C22 H30O4. And that's going to produce carbon dioxide plus our THC. So that'll be C21 H30O2. This carbon dioxide will likely be a gas, might be dissolved actually in the THC oil itself, and then kind of burn off. So it might be dissolved. And then our THC and THCA are an extremely viscous liquid, but I would call them a liquid. So I'd put phases there of liquid. And this should be balanced as it is. We have 22 carbons on both sides, and we have 30 hydrogens on both sides, and we have 4 oxygens on both sides. I'm going to use a highlighter and point out what the changes that's taking place here. Our carbon and our oxygen right here are becoming carbon dioxide and separating from the rest of the THC molecule. Now, this carbon, I'll highlight this blue right here, is going to form a new bond. It's currently bonded to a carbon, but it's going to form a bond to a hydrogen. Either the one here on this carboxylic acid or bonded to this oxygen, or from a nearby water molecule, right? So I can pull off something like this. Maybe it's one of those. And so what we have here, if we kind of blow this up, the change that's taken place is now this carbon is double bonded to another carbon, and another has a hydrogen in place of the carbon used to be bonded to so right here, a carbon with a double bond to an oxygen, and then a single bond to an oxygen bonded to a hydrogen. And just that small piece of the THC molecule is enough to change its overall shape and structure. So that way it actually interacts with your body differently. It makes it harder for it to cross the blood-brain barrier. It's because it increases the polarity of that molecule for one, and it just makes it a different shape and with a larger size. And so this reaction will actually happen slowly over time. So just leaving a pile of THC around, it'll slowly convert into THC, to the point where if you had a crystal of THCA, you would actually struggle to characterize it to be 100% THCA, just because some of it will always be decomposing into THC. So time alone is all you really need to make this happen. However, you can accelerate the process with heat. While it'll happen quickly with heat, it won't happen at a 100% conversion. So not absolutely all of the THCA will become THC, just a percentage of it. And so if it's vaporized or smoked, and vaporized while being smoked, the molecule will convert into THC, which is the more psychoactive version, although the conversion won't be 100%. So we might characterize that acceleration by heat by putting a little heat symbol over the top of our arrow if we wanted to communicate that this reaction was happening quickly because heat was applied. All right, let's look at another one. So here is THC, and it's decomposing here through oxidative decomposition. Big word, I know. CBN, which is a little bit different. Um, and so in this, the real difference that I want to point out is in this part of the molecule in this ring right here. What's happened is that some of our carbon atoms in that ring have lost a bond to a hydrogen and formed a new bond to carbons. So I'm going to draw this out actually below it, just this one little ring. So I'm going to kind of blow up this section right here. So just kind of blowing this up, I want to point out what's changing here. We are creating some double bonds in between carbon atoms. And to do that, we have to lose a hydrogen that's bonded to each of these carbons around this six-membered ring. And so in these cases, these bonds are going to break, which I'm going to show with a little cleave sign like this. And we're going to form some new bonds between the two carbons where these hydrogens are lost. And so that's going to create a alternating double, single bond structure here that is actually extremely stable. And so we can kind of think of also producing this as creating two hydrogen diatomic molecules. Um, because so for each of these, what will happen is we'll lose one of our hydrogens, and then the electrons that are part of this bond here. Oh, sorry, that was brutal. The electrons that are part of this bond here will become the electrons that are the double bond between the two carbons. And then to maintain our octet rule, these hydrogen to carbon bond between these two will become part of the hydrogen. And so we're essentially shuttling electrons around in these oxidative decompositions and creating a more stable ring structure within our THC molecule. Anytime we have one of these alternating double, single bonds, we have a lot of stability that comes with it in the molecule. We call these conjugated double bond systems, and they're a little magical in that way. So the THC is decomposing into a more stable molecule overall, similar to how the THCA molecule decomposed into THC. It was less stable, and it decomposed, or it decarboxylated into something more stable. So this will happen with just time. So it'll be just time will do this. And so that means that any either flour or concentrate product that is left alone for a really long time will actually have a lot of that THC convert into CBN, which is not psychoactive. If I was going to write out this chemical equation, I would to kind of highlight, the loss there of our hydrogens, I would start with the chemical formula of our THC molecule. 21. So 21 carbon, 30 hydrogen, and 2 oxygen. And it'll decompose, separating. So decomposition, we're going to separate out some of our molecules into our 2 hydrogen molecules, and then our CBN, which is going to be a carbon with 21 carbons. And we're losing 6 hydrogens, so we'll have 26 hydrogens, and we still have our 2 oxygen. And this should be balanced because the 4 hydrogen lost from going from 30 to 26 are captured right here in our 2 hydrogen molecules. Our next reaction that I want to look at is isomerization. So an isomer means that you have 2 or more structures that have the same chemical formula. And the difference is how their bonds are arranged. And so they're all connected in the same order, but double bonds or lone pairs might be rearranged in a different way. So let me label these ones. We have a few molecules out here. So this is delta 9 THC. And the 9 is referring to the placement of the double bond in this top ring right here. And so really saying that this is carbon 9 in our overall structure, if you were to number all of the carbons in the THC molecule. Right here is delta 8 THC, and this is delta 10. And it's really the only difference is the placement of where this double bond is right here in this ring. Everything else is the same in our like molecular structure. And so all of these have the exact same chemical formula. They're all C21H30O2. The difference between these, again, is that shifting of the double bond, which means that the hydrogen, so I'll draw out delta 9 a little bit bigger and show what's breaking and what's not. Okay, so so this one's delta 9, and if I wanted to convert it into delta H THC, I would need to lose one of these hydrogens, and my double bond would move over to, let's highlight this a little differently. This double bond right here would move over to between these two carbon, and I would need to add a hydrogen at my carbon that used to have a double bond. And so that's going to then produce so just focusing on that top part, a double bond between our carbons and a loss of a hydrogen, and then a single bond where there used to be a double. And so this shift from one location for the double bond to another is typically requires a series of chemical reactions, usually heat and a catalyst, like an acidic catalyst is involved. Typically what happens in the cannabis industry is there is a desire to not have any delta 9 THC, which is a controlled substance and illegal in some states. And so CBD, if it is legal in the state, is converted into delta H THC. And you can do that by heating up the CBD into in a solution of non-polar solvent like toluene with an acid catalyst, and you can convert that into the isomers of THC. The problem with this is there's very little regulation on how these are tested in these marketplaces that don't have rigorous testing standards in place when they're not in when delta 9 THC is not legal. And so a lot of times these products can have either high pH or low or high pHs if they weren't properly distilled and isolated from the reaction mixture. And they can also have a lot of side products as well, like all the toll and maybe even heavy metals and things like that if a metal catalyst was used, or bits of the acid or the solvent. And there's not a lot of research on what inhaling things like olivetol, sorry, it's hard to say, would have on someone. And so it's kind of this like, it's unregulated essentially. And so consumers aren't 100% sure what they're getting in the product, which is a reason why, in general, there's some concern about the Delta H prevalence, or especially it being synthesized from CBD, just because the marketplace and the regulations around proving that your products have exactly what you say it has and nothing else is still a gray area. So this isomerization reaction here between these is something that can be catalyzed with an acid. And delta 8 THC is less potent than delta 9, and delta 10 is believed to be even less potent. There's also delta 6. And so these isomers of where this double bond is, it's just changing that location, but the overall chemical formula is the same. And so these are hard to separate if you have a mixture of them. But you can do it through some forms of chromatography and distillation in brought together. So thinking about olivetol a little bit more, let's talk about the synthesis of CBD or THC from a terpene. This is kind of the newest thing that I've seen, which is where CBD is synthesized from orange peels. And really what's happening is they're using terpenes like limonene to combine with alvetol, which is this right here. Let me write it out for you since it's so hard for me to say. I think I spelled that right. So this chemical formula here is C11 H16O2, and then our limonene is going to be C10H16. So you can imagine taking orange peels and extracting out and distilling and isolating the limonene from it. Combining that with the alvetol will give you something like CBD, and with heat, you can actually, or an acid catalyst, you can convert that into THC. So let's see if we can find these molecules in our CBD. So here's CBD. And here's our chemical formula for it, C21H30O2. So let's use limonene in green. So you can see this is right here in our CBD molecule. And our alvetol is right here. And so what we've really done is we've connected our alvetol from this carbon right here and formed a bond with this carbon right here. And so these have connected. And that's this right here. Right? So when you see something advertised as a CBD product that's not from hemp or from cannabis, what's happening is they're using a synthetic procedure that's bringing together two molecules that have no THC in them at all to create CBD or to create THC. And so you can do this with this process with other terpenes as well. Limonene is particularly straightforward and plentiful if you have a pile of orange peels. And alvetol is also a really common synthetic precursor that's used in a lot of different things. And so it's also readily available. Edit out that again, like our isomerization or our production from CBD to form delta 8 THC, this process isn't as regulated as for producing products that are edit. So similar to forming delta 8 THC from CBD, this process is in a legal gray area right now. It has no THC in the CBD produced from the alvetol and the limonene, theoretically. And so you can actually make this in a way that skirts around laws that prevent you from producing delta 9 THC. But there aren't there isn't a robust legal process or regulations around reporting what is and testing what is in the products being sold as this. And so you might have excess alvetol around and other byproducts from the chemical reaction that's used to make this. And so again, you aren't 100% sure exactly what you're getting, even though it's really interesting to see CBD advertised as from oranges without any THC in it. So, last reaction we'll look at is the conversion of CBD to THC. So, in this one, we again have the same chemical formula. So, if I was going to write this out, it would look like C21H30O2 forming C21H30O2. But the structures look really different. So, these are not isomers because we have a different set of we have a different set of connections between our atoms. And the important part here is really at this piece right here. This carbon right here forms a bond to this oxygen right here. Like that. And so we can see that carbon's right here, and here's our oxygen. So then the carbons that you see right here and right here, these are the two carbons that are coming off of this carbon adjacent to the oxygen. And so our hydrogen is essentially transferring from the oxygen that it's bonded to the carbon that used to have a double bond to it. And so what happens is we're essentially closing and creating a ring structure within the molecule. And so to make this actually happen, we need a catalyst, and we need an acid catalyst. And so if we have a catalyst, we typically write it on the top of the arrow. A catalyst means something is used but then reformed in a chemical reaction. So there's no net change to it, even though it changes and then it changes back, and it can be used again and again. So here, this is acid catalyzed. And this acid catalyzation, usually this has to be a strong acid. And so you have to get a pH really low. And so the process of converting THC or CBD into THC is something that is discussed like as, well, what if it happens in your stomach? Like, what if I take CBD and it converts into THC in my stomach with my digestive juices? And, or can I mix my CBD with a lot of acid and then produce THC and then consume it? And so we'll discuss this in class and talk about kind of the policy implications about how people are sometimes instructed not to consume CBD even if it's beneficial because it would show up as THC in a drug test or something similar. So we can make this is a reaction we can catalyze with an acid, and we'll explore whether or not we think that this is something that is dangerous to people who need to have 0 THC present in a blood sample.